Good evening, sir. My name is C. Nikila. I am from ECE department. My roll number is 2340180481. My assignment topic is characteristics of microprocessor. What is microprocessor? A multiprocessor system integrates two or more processors within a single computing environment, allowing them to work collaboratively on tasks. These processors share system resources, memory, I/O, and internet connections, networks, enabling parallel computations and enhanced performance. Multiprocessors from the foundation of the modern computing, from smartphones and laptops to enterprise servers and supercomputers. Parallel processing, shared resources, improved performance. Parallel processing, multiple tasks execute simultaneously. Shared resources, processors access common memory and I/O. Improved performance, throughput and responsiveness increase. Memory architecture comparison, shared memory, distributed memory, symmetric multiprocessing. Symmetric multiprocessing feature identical processors with equal access to shared memory, I/O devices, and system resources. Each processor can execute any task, providing flexibility and simplicity. SMP excels in general purpose computing but faces scalability limits due to contention and bottlenecks beyond 8 to 16 processor. First one, uniform memory access, single operating system, bus architecture. First, all processors experiences identical memory latency, and second one is simplified management and resource allocation, and third one, processors communicate through shared system bus. Non-uniform memory access. NUMA system partition memory into local and remote regions. Processors access local memory quickly but experience higher latency accessing remote memory. This architecture enables superior scalability to 64 plus processors by reducing memory contention through software must optimize data placement to achieve peak performance. Local access, remote access. Local access, latency, bandwidth responses. Remote access, higher latency, lower bandwidth, performance penalty. In this slide, I will explain cache coherence protocols. When multiple processors maintain private cache sharing, memory coherence protocols prevent inconsistent data, write invalidate and write update strategies, synchronize cached copies across processors. Protocols like MOESI track cache lines, states modified exclusive shared invalid to maintain system correctness while minimizing communication overhead. Modified exclusive invalid shared. Internet connection networks. The internet connection from the communication backbone connecting processors, memory modules, and I/O devices. Topology choices but ring mesh, torus, hypercube, balance, cost, latency, and bandwidth. Modern system employ hierarchical network with local high-speed connections and global routine, managing billions of data transfers per second while maintaining low latency. First one, bus, simple limited bandwidth. Second one is mesh, scalable moderate latency. Third one is hypercube, high performance complex routine. In this slide, I will explain about scalability challenges. Scalability faces three critical barriers. Memory contention limits bandwidth as processors grow, cache coherent traffic explodes, requiring sophisticated protocols and synchronization. Overhead barriers unlocks serialized execution. Solutions include NUMA architectures, distributing caching strategies, and lockless synchronization techniques. However, Amdahl's law reveals that sequential proportion fundamentally limited parallel speedup. First one, memory bandwidth, coherence, overhead, and third one, synchronization cost. Memory bandwidth, shared memory bus becomes congestion point. Second one is protocol traffic grows non-linearly. Third one, log contention serializes critical section. Performance matrices. Evaluating multiprocessor performance requires three key metrics. Instruction per cycle IPC measures execution efficiency within each processor. Throughput qualifies total operation completed per unit time across all processors. Latency measures response time for individual operations. Effective multiprocessor design optimizes all three while managing power consumption and cost constraint in modern 3 to 5 range IPC range 10 to 100x speed up target 10 to 100 ns memory latency. Future trends in multiprocessor systems. Emerging multiprocessor technologies reshape computing. Heterogeneous architectures behind CPUs, GPUs, and specialized accelerators, chiplets design and connect smaller processors for modularity and yield. Advanced coherence protocols handle exascale systems and neuromorphic approaches mimic brain architecture for specific workloads. Artificial intelligence and machine learning drive demand for massively parallel systems while power efficiency becomes paramount in edge computing and data centers. First, chiplet revolution, neuromorphic systems.